This is Analysis of Time Series, Chapter 7, Introduction to Time Series Analysis in the Frequency Domain. And so we're going to start looking at frequency components of time series data. We're going to start by relating this to eigenvalues and eigenvectors of a stationary covariance matrix. And we're going to see how sines and cosines naturally fall out of that. And then we're going to look at methods that build on that. So a time series data set, like any other sequence of numbers, can be written as a sum of sine and cosine functions with varying frequencies. This isn't a special property of time series data. It's basically like in vector algebra, changing the basis to a basis of sines and cosines. And this is called the Fourier representation or Fourier transform of the data. And the coefficients corresponding to the sines and cosines at each frequency are called the frequency components of the data. Now, it turns out that with time series data, for reasons that we'll be discussing, this sine and cosine representation has some really useful properties. Looking at which frequencies have large and small components can help identify appropriate models. Sometimes it's helpful to think of sound, right? You can think of sound as just a time series of amplitudes, but it's very natural to think of sound in terms of frequency components. Looking at the frequency components present in our models can help assess whether they're doing a good job of describing our data. So we want to look at what the theoretical frequency components should be for a given model under consideration and compare them to the frequency components observed in the data. Okay, so we're going to review some material on eigenvectors and eigenvalues and see how that fits in. The eigen decomposition also arises elsewhere in statistics, such as principal component analysis. So you may be you may have been seeing this in other stats courses. So we have a univariate time series model, and that's a vector-valued random variable y1 through n, which has some covariance matrix V, and V is an n by n matrix with entries Vmn. Now, a kind of linear algebra property of V is it's a non-negative definite symmetric matrix. And so we know it has n non-negative eigenvalues, which we call lambda1 through lambda n. And then it has corresponding eigenvectors u1 through un, such that VUN is lambda n un. That's the definition of eigenvector eigenvalue pairs. And for these non-negative definite symmetric matrices, these eigenvectors are orthogonal. So that means UM transpose UN is equal to 0 if M is not equal to N. And it's often convenient to work with normalized eigenvectors scaled so that their absolute value is 1. Now, this eigen decomposition, the orthogonality of the eigenvectors, has the consequence that the components of y in the directions of different eigenvectors are uncorrelated. And if we want to do the little algebra to check this, if we know that the covariance of AY with BY is A cov YY B transpose, and then if we set A and B to be the eigenvectors, we can take them outside the covariance, use the property. Here we're really also using that left eigenvectors are the same as right eigenvectors, and then the orthogonality of the eigenvectors is exactly what we need to show that the components in those directions are uncorrelated. So this has the feature that if we knew V, we could convert the model to a representation where the observable random variables are uncorrelated. V has V, it's an n by n matrix. In general, it's going to be hard to know. So that's why we often assume IID. If things are IID, then we know V is diagonal with just a term sigma squared down the diagonal. Okay, so the nice thing about time series analysis, which we're going to see, is that we do know what these eigenvectors are. They're essentially the sine cosine basis. And so we can map to that basis, and then we live in a happy, uncorrelated world. If things are Gaussian, then uncorrelated implies independence. So that's even more convenient. Now, we're going to take a kind of empirical approach to starting to understand this. We're just going to use numerical linear algebra to calculate the eigenvectors for the covariance matrix of an AR1 model. Let's pick n is 100. The AR1 parameter phi is 0.8. And then we can just use the eigenfunction in R to plot what these eigenvectors are. And when we do that, here I've plotted the first 5 eigenvectors on the left and the second 5 on the right. If we plot them, we see they are strikingly sinusoidal. And so that gives us a clue that these kind of sine waves are going to play an important role. And if we look at the eigenvalues are decreasing. And the way this was set up, the largest eigenvalues correspond to the longer sine waves. As the frequency gets higher and the sine waves get more compressed, the eigenvalues decrease. Okay, so we can wonder whether these sinusoidal eigenvectors are a special feature of the AR1 model or something more general, and that's what we are going to take a look at. Let's just suppose that we have a long stationary time series model. Well, what do we know from stationarity? If Yn is stationary and has an autocovariance function gamma, then gamma h, and well, we can write the covariance between time m and n just as depending on h, which is m minus n. And so if we write this out in the full form, where capital gamma is the matrix of covariances, we're going to be a little bit fast and loose with moving to infinity here. So sometimes it'll be convenient to imagine that we can work with infinite matrices, but we're not going to think clearly about what that means or how that's defined in a limit. We're focusing on the concepts rather than the details. Okay, so an infinite eigenvector corresponding to this infinite matrix gamma is going to be a sequence such that gamma u is lambda u. Or if you write out matrix multiplication explicitly, and again, you don't worry too much about the infinities, then you have gamma mn un is lambda um when you sum up over n for all m, and that is the that's what it means for u to be an eigenvector for gamma with eigenvalue lambda. And based on the numerical exploration we did for the AR1 model, we're going to look for a sinusoidal solution. Un is e to the 2 pi I omega n. Here, omega is in cycles per unit time. We have another option here. We could write un is e to the 2 e to the e to the I nu n, this saves a factor of 2 pi. Nu then is called angular velocity in radians per unit time. And it saves a little bit of ink to write nu instead of 2 pi omega, but cycles per unit time is a standard measure of frequency. Now we get to do some algebra. So when we write out the sum of gamma mn un, and we take advantage of the fact that gamma mn is little gamma m minus n, if we set h is m minus n, then we can switch it to gamma h u m minus h, and then when we substitute in u m minus h for e to the 2 pi omega m minus h, we see that this factor of e to the 2 pi omega m nicely comes outside, and what we have left in the sum is gamma h e to the minus 2 pi I omega h, which is then some constant that depends on omega. And so that's the eigenvalue, and the 2 pi I omega m that we had pulled out is exactly the eigenvector. And if we want to check that this shows that un is the eigenvector and that this works for any choice of omega, I mean, essentially, all we can say is that this argument holds for any omega and it matches the definition of eigenvector and eigenvalue for matrices, at least if we ignore issues related to infinite sums, which here our main goal is to get the intuition, so we can do that. Okay, so we now have an expression for the eigenvalues, which is this thing, lambda of omega is the sum of gamma h e to the minus 2 pi I omega h. This has a name. It's called the spectral density function, viewed as a function of omega. And this also has a name. It's called the Fourier transform of gamma h. Now, when you look at equation 6, it may, if you've seen the Fourier transform in applied math or engineering classes, you most likely have seen what's in equation 7, where you write an integral rather than a sum. And so I'll just point out that these are really the same thing, because if you think of the autocovariance function gamma h, it only takes values at integer values. And so if you put gamma of x, where x takes masses at point values, at integer values, then the integral turns into a sum and you get exactly 6 back again. So this is the regular Fourier transform. Now, it's convenient when you're doing the math to use complex numbers and complex exponentials. You don't have to. You can always view things in terms of sines and cosines, and the complex numbers just keep a convenient way to keep track of the sines and cosines. If gamma h is real, then we get 2 real eigenvectors, cos 2 pi omega n and sine 2 pi omega n, and we have real eigenvalues, obviously. Now, it's, depending on how comfortable you are with complex numbers, you may or may not want to think in terms of complex numbers. Here's just a little exercise. If you want to make the transition between the complex numbers and the sines and cosines, it's all based on this identity that e to the 2 pi I omega is cos 2 pi omega plus I sine 2 pi omega, which you could, if you wanted to, construct Taylor series approximations to check this. Oops. Why is my pen not working? Okay. There you go, construct Taylor series. Expansions of each term, and if you want that little exercise in Taylor series expansions, that's worth doing. Okay, so at least up to addressing possible regularity conditions to do with infinite sums, we found that the eigenvectors for any long stationary time series model are approximately sinusoidal. And then when we're in a finite time series situation, we're only going to have n eigenvectors because we have n data points, we have an n by n covariance matrix. And so let's think what these are. Well, we have one eigenvector for omega is 0. We have 2 eigenvectors corresponding to sine cosine pairs, and these arise at the frequency omega n is n over big N, where little n runs between 0 and n over 2. If n is even, then we get one final eigenvector with frequency 1/2, and that gives us our n basis vectors for the n-dimensional space that make up the Fourier basis. So we now have the time series data, which is called the time domain representation of the data. And if we just change basis to this Fourier basis, we get what's called the frequency domain representation of the data. And, they're really just different ways of looking at the same thing, and they're convenient for different things. And we want to learn to use both ways of looking at the data. Now, one of the things that's convenient for looking at the frequency domain representation, it turns out we can calculate the frequency components relatively easily. So the frequency components are the components in the direction of these eigenvectors. They're just have this form here. Cn and Sn in capital letters are what happens when we take the frequency components, or the real and imaginary parts of the Fourier transform, corresponding to the model, little cn, little sn are going to be the same things done to the data. And one thing to note here is we've done things just a little bit differently from the regular Fourier transform. We've stuck in this factor of 1 over root n. We've done a different scaling. You may be able to guess why the 1 over root n scaling is going to be convenient. So, right, the 1 over root n turns out gives a central limit theorem. We have n terms in a sum, and they're going to have mean 0 under appropriate stationary model, and so we might hope for a central limit theorem at a 1 over root n scaling, and that's what we get. Okay, so the link between those sine and cosine components and the Fourier transform is made explicit here in this discrete Fourier transform, and we call that dn, and it collects the sine and cosine components together. Now, it can be awkward when you see different representations of the Fourier transform, because you have different choices about where to put factors of 2 pi, or sometimes people will put in a factor of root 2 pi. Sometimes, as in here, we have a factor of 1 over root n. So you have to be a little bit careful about these. They're just constants in some sense. They don't really make any difference. But of course, to get your numerics right, you do need to pay attention to the constants, even if they're conceptually not so important. So for example, when you're in R, if you ever find yourself calculating a discrete Fourier transform directly, you'll do it through this function FFT, stands for fast Fourier transform, and FFT does not include this constant. So you need to add it in yourself if you want to match the results that we're doing with that constant. So FFT is an implementation of the fast Fourier transform algorithm. This is a really nice algorithm. It enables computation of all the frequency components in order n log n computation. And historically, that's another important reason for using the frequency domain, because particularly when computation was at more of a premium, things that order n log n is really surprisingly attractive rate. Superficially, it may even surprise you that this is possible, right? Because if you think of what you have to do, the way we've developed this idea of thinking of the Fourier transform, it's a change of basis. It's essentially a matrix multiplication, and so you need to work with an n by n matrix, and you need to multiply an n by n matrix by an n by 1 vector. And so you might think the most immediate way to do that would involve order n cubed additions and multiplications. Now, even with modern computing, if you have a long data set, if you have n is 10 to the 5 or n is 10 to the 6, then n log n becomes computable, whereas n cubed becomes hard or impossible. Now, this 1 over root n scaling works for all frequency components except the 0 frequency. So the 0 frequency has a mean mu is expected yn. Other components have mean 0. This isn't such a problem in practice, because in practice you subtract off a mean before computing frequency components, and that's equivalent to removing the frequency component of frequency 0. Basically, when you're looking at frequency components, you don't normally think of the mean as a frequency component, even though formally it is one. Now, we've seen that the frequency components are asymptotically uncorrelated, and we've already argued that maybe this 1 over root n scaling might give a central limit theorem, and it does. And so we've really got two things by moving to the frequency domain. We've decorrelated the data, and we've also got normal frequency components that are normal from a central limit theorem. They're asymptotically normal, even if the original time series model is not Gaussian. And so in the frequency domain, statistical techniques based on independence and normality are appropriate. And so that's really a nice thing, because when you're in the time domain, you often find yourself making normal approximations or white noise approximations when you're not really sure if they're justified. Whereas in the frequency domain, at least asymptotically, they are justified. We should write out this normal approximation for the frequency components. Here it is. The sine and cosine components are approximately independent, mean zero, normal random variables with variance half lambda of omega n, where lambda of omega n is the spectral density at omega n, and omega n is this discrete frequency n over big N. Okay, and so then if we sum and square these things, we get that the sum of squared sine and cosine components at a given frequency has a chi-squared on 2 degrees of freedom distribution. We often want to sum and square the sine and cosine components. If you have a stationary time series, there's no particular reason. The sine and cosine components are basically shifts in time. Shifts in time don't really have much meaning for a stationary time series model. So the total power at that frequency, which is the sum of the squares of the sine and cosine components, has more meaning. And in equation 13, we see that has a nice expression, chi-squared expression from the central limit theorem. A nice thing happens when we take logs of 13. So if we log the summed squared frequency components, then we separate the chance variation, which is a log chi-squared, from the log spectral density. And so we have an additive representation, which is convenient for estimating the log spectrum. So there's multiple reasons for calculating the log spectrum rather than the raw spectrum. And the statistical reason is given by this equation 14, that it gives you a nice additive noise model. And that leads us to the periodogram, which we will discuss in the next section.